Okay, so this is what we learned last time. And so we talk about consistency of a method, and then we define consistency by limit of the residual error at xn plus k divided by h goes to 0 is equal to 0, right? If and only if the method is consistent. And then from that, we prove that consistency is equivalent to the condition rho of 1 is equal to 0 and sigma of at 1 is equal to rho prime of at 1. Right? So where rho is the first characteristic polynomial and sigma is the second characteristic polynomial. Right? So we have seen that. So now what we are going to do is we are going to see the relationship between this and the order of the method. Right? So I will write that as another exercise. Exercise. So what we are going to prove is we are going to prove that now the method is of order 1, at least order 1, right? So if and only if the conditions are satisfied, right? So these conditions, that is rho of 1 is equal to 0 and sigma 1 is equal to this. So that is this condition, right? So we are trying to relate that condition with the order of the method. So we shall prove this first. Right, so you know that order is at least 1 is equivalent to C naught is equal to 0 and C1 is equal to 0, right? So if the order is 1, right, meaning order is 1, then C naught and C1 should be 0 and C2 cannot be 0. If the order is 2, C naught, C1, C2 are 0, C3 is non-zero. So in any case, as long as the order is at least 1, C naught and C1 should be 0, and vice versa also, right? If C naught and C1 are 0, then you clearly know that order is also at least 1. So now you know the formula for C1, that is J is running from 0 to K, alpha J is equal to 0, and summation of J is equal to 0 to K, J times alpha J minus beta J is equal to 0. Right, so that is the definition of C naught and C1. So this clearly, if and only if J is 0 to K, alpha J is equal to 0, and summation of J is equal to 0 to K, J times alpha J is equal to summation of J is equal to 0 to K beta J. So this is equivalent to first characteristic polynomial at 1 is equal to 0, and this one is derivative of first characteristic polynomial at 1, and this is second characteristic polynomial at 1. So we have shown that if the order is at least 1, then rho of 1 is equal to 0 and sigma 1 is equal to rho prime of 1. So now we have a short way to check the consistency. because there we prove the consistency if and only if rho 1 is equal to 0 and sigma 1 is equal to rho prime 1. But here we say that the order is at least 1 if and only if rho 1 is 0 and rho prime 1 is equal to sigma 1. So that means consistency is equivalent to order is at least 1. So I will write that as a remark here. By the above two results, right? So we get right. So the method is consistent if and only if order is at least 1. So if they want you to check the consistency of the method, you just need to check the order, right? So if you check the order and if the order is greater or equal to 1, then clearly you can say that the method is consistent, right? So for example, right, so if you look at Euler method, yn plus 1 is equal to yn plus 1 minus yn is equal to 8 times f of n, right? So for this, you already know order is 1, right? So this means that is consistent. Right, so in all the examples we did earlier, right, so you can see that all of them has order as at least 1. So we can clearly say all those methods are consistent. Okay? So that is what we have. So once you do consistency, so that means the method is basically computing the results in a consistent way. But the important thing we need about numerical method is we want to reduce the error. That means we want to guarantee the convergence of the method. So we need to make sure that the method is convergent. That is what we usually do in numerical analysis, right? So in numerical method, we try to see the method is convergent. So here also, we will always try to reduce the error at the end. So here, in order to reduce the error, we need to have convergence of the method. But in order to do the conversion, we need to have something else. Right? So that is called zero stability. Right, so we are going to define a new concept called zero stability of the method. Right? So we already defined conversion. We first define order, and then we define conversion, and then we define order first, and then consistency next. Now we are going to define zero stability, and by using all these three, we are going to define the convergence. Right? So we will say what do we mean by zero stable. Again, we consider the linear multi-step method. I consider Right, so we define the method, right? The linear multi-step method as we usually define, right? And we say that the method is zero stable, right? Said to be zero stable if okay, so this is how we define the zero stability. Right? So the way we are defining the zero stability is first we write down the characteristic polynomial. First characteristic polynomial, rho of z. Right? So that is the first thing you have to do. When you want to check the zero stability of the method, right, you write down the first characteristic polynomial. After writing down the first characteristic polynomial, you factor it or you try to find the roots of the first characteristic polynomial. Right? So after finding the roots, you have to take the modulus of all the roots. Right? So you take the modulus of all the roots. And if all the roots are of modulus less or equal to 1, that is, if the roots are between -1 and +1, then what you have to do is to, if all of them are between minus and +1, then you have to check whether there is any roots which are of modulus 1, that is whether there is -1 or +1 in the root. And if there is one such root, you have to make sure that that is only one root. Right? So you cannot have +1 and +1 as the root. You cannot have -1 and -1 as the root, right? In order to have zero stability. So that is what you have to check. First thing, you have to write down the characteristic polynomial. Second, you find the roots of it. Third, you check the modulus of the roots. Right? and if at least one of the roots is bigger than 1 or minus 1 less than minus 1, so if the modulus is at least one of them is bigger than 1, then you can immediately say no zero stable. Right? If all of them are between minus 1 and plus 1, that is if all of them has absolute value less or equal to 1, then you have to check what are the roots which have absolute value equal to 1, and then you have to see whether they are simple or not. So that is what you have to do. So let me give you a few examples. And so first look at this example. So here the order is 2, the step is 2, k is equal to 2, and so you can write down what is alpha 1, alpha 2, alpha naught, alpha 1 and alpha 2, right? Because you only need the first characteristic polynomial. So clearly you know alpha 2 is 1, alpha 1 is 0, alpha naught is minus 1. So after writing the alphas, you can write the first characteristic polynomial. And so rho z is equal to summation of j is equal to 0 to 2, right? Alpha j z to the power j, that is the first characteristic polynomial. Right? So when you put alpha naught, okay, so this basically is z squared minus 1, right? Because alpha 2 squared plus alpha 1 z plus alpha naught. So alpha 2 is 1, z squared plus alpha 1 is naught plus alpha naught, that is minus 1. So that is z squared minus 1. So you know, next you find the roots of it. And rho is equal to 0 gives you z is equal to minus 1 and plus 1. Because z squared minus 1 is equal to 0 is z minus 1 into z plus 1 is 0. So z is plus 1 and minus 1. So clearly both of them are of less or equal to 1. Absolute value less or equal to 1. Right? One of them is plus 1 and one of them is minus 1. Right? So both of them are of lesser modulus less or equal to 1. Right? So clearly less or equal to 1. Right? So in particular, in both cases, actually both of them absolute value equal to 1. Right? So clearly all of them are less or equal to 1. So first condition is okay. Now you check whether there is anything equal to 1. Yes, both of them are equal to 1. But fortunately, they are different roots. Minus 1 is a different root, plus 1 is a different root. There is no repeated roots. Right? So both are simple. Right? So both of them are simple. So clearly you know that this method is zero stable. Right? This is Right, so clearly the method is zero stable. So here one example we check zero stability. Now I will give you one couple of more examples. Right, so a couple of more examples. Now this example, right, so if you look at this example, yn plus 2 minus 2yn plus 1 plus yn is equal to h times fn. And so here you can write the characteristic polynomial. Right, so I don't need to write everything again. So rho of z is equal to alpha 2 z squared plus alpha 1 z plus alpha naught. Right, so if you write down the characteristic polynomials, right, you can immediately see, right, so alpha 2 is 1, alpha 1 is minus 2, alpha naught is 1. So this is the characteristic polynomial. So roots are if you solve this equation, that is z minus 1 quantity squared is equal to 0. So z is plus 1 and plus 1. And both of them are plus 1. Right? So you know that z is lesser or equal to 1. Right? Especially, you know absolute value z is 1. And plus 1 is not simple. Because there are two plus 1s, plus 1 and plus 1 again, right? So there is right, so there is plus 1 and plus 1. So that is no repeated roots. Right, so there is repeated roots plus 1 and plus 1. So this is not a simple root. So even though the roots are all of them are less or equal to absolute value less or equal to 1, because the roots are not simple, this cannot be zero stable. Right? So not zero stable. So this method is not zero stable because of this condition, right? So not the root is not simple. Now let me give you another example. And so now if you look at this numerical method, right? So linear multi-step method, you can see that yn plus 2 minus yn plus 1 minus 2 times yn is equal to 8 times fn plus 1. So you can check the first characteristic polynomial, that is z squared minus z minus 2. Okay, so that is z squared minus z minus 2. Right. So rho z is equal to 0 will give you z is equal to 2 comma minus 1. Right? So if you look at the roots of this polynomial, it is z minus 2 into z plus 1. So 2 comma minus 1 are the roots. So here one of them is less or equal to 1, absolute value minus 1, absolute value is equal to 1, so that is fine. But 2 is clearly greater than 1, right? So absolute value of 2 is clearly greater than 1. So you know that that condition is not satisfied. Right? So here because of this is not zero stable. And so now I gave you 3 examples. One of them gives you a zero stable method. The other two are not zero stable for different reasons, right? This one is not zero stable for a different reason, and this one is not zero stable for a different reason, right? So this is how you check whether the method is zero stable or not. So now by using the zero stability and consistency, we are going to define the convergence of the method. Right? Okay, so now convergence. Right, so we say that the method is consistent if it is, sorry, the method is convergent if it is zero stable and consistent, right? So if you want to check whether the method is convergent or not, you have to check whether the method is consistent and zero stable, right? So you have to check both of them, right? So we will do one example which you may expect in the exam paper from this type of a part, right? Because uh, checking consistency and checking zero stability we have done already. So here if you want to check convergence, you have to do the same thing again, right? So you have to check the order and you have to check the roots of the first characteristic polynomial, that you know. Right? So I will do a slightly different type of problem where we talk about convergence of a method. Okay, so a linear multi-step method is given like this. right? So this is the linear multi-step method, right? So here the coefficients are given in a variable a, and you can see that they are not numbers. Now they have a in there, right? A plus 1, a minus a plus 2, h over, so a plus 5 over 2, a plus 1 over 2. These are the values, and so you can answer different questions based on that. And so first part, and so I gave you two parts here. First part, they ask you to find the values of a, right? So a is given here, and so I put the inverted comma so that you know what is the a we are talking about. And so it is the a given in the problem. So we want to find the rate for a, or the values for a for which the method is convergent, right? And second part, they ask you to find a minimum order that is independent of a, because you know, because of a in these coefficients, right, alphas and betas are now depending on a. You know that when you try to find the order, you might have to be depending on a to make some c I 0, right? So sometimes to make c naught 0, you need to have certain values for a. To make c1 0, you need to have certain values for a. So we will check up to which point we can go without changing anything on a, right? So that is the second part, but we will do the first part. And so you know alphas and betas, so I am not going to rewrite all of them again. So to do the first part, first we have to find the order, because they say convergent. So you know consistency and zero stability you have to check. So for consistency, you need to check order, right? Order should be at least what? So you need to make sure that you have C naught and C1 are 0. Right? C naught is summation of alpha j, right? So that is 1 plus a plus 1 minus of a plus 2. Right? Alpha 2 plus alpha 1 plus alpha naught. Right? So that is clearly 0. So you all know that. That is 0. Next C1. C1 is j alpha j, right? So that is 2 plus a plus 1 minus beta j, right? 2 alpha 2 plus alpha 1 minus beta naught beta 1 beta 2, right? So that is a plus 5 over 2 plus a plus 1 over 2. Right? So that is a plus 3 minus There also 2a plus 6 over 2, that is a plus 3. So this is also 0. And these two results are true for all a. Right? So you can easily check that C0 and C1 are 0 for all a. Right? So even though whatever number you put for a, C1 is always 0. Whatever number you put for a here, C0 is also 0. So order at least 1. And so you clearly know order at least 1. So consistent. So that part is okay. Consistency you prove. Right? For all a, it is consistent for all a. Right? So that's true. Now you need to check the zero stability. To find the zero stability, you have to write down the first characteristic polynomial. Okay, to find the zero stability, you find the first characteristic polynomial. Rho of z is equal to z squared plus a plus 1 z minus a plus 2. Right, so you have this as the first characteristic polynomial. Right, and z squared plus a plus 1 z plus a plus 2. Right, so you can find the roots of this. Right, so that is not a big deal. You can easily try to find the roots. Right, so you factor, or you can, whatever method you use, you can use. Right, I will write down the roots. Right, so that become z is equal to 1 and z is equal to minus of a plus 2. Right, so these are the roots of the polynomial. So one of them is a number 1, so that is obviously less or equal to 1. But for zero stability, you need to have this to be absolute value of this to be less or equal to 1. Right? First condition, all the roots must be absolute value less or equal to 1. So this one is less or equal to 1. Right? So that means a plus 2 is less or equal to 1. Right? So this gave minus 3 less or equal to a less or equal to minus 1. Right? So a is between minus 3 and minus 1. Right? But one more thing you have to check, if the root absolute value is 1, then you have to make sure that the root is simple. So you have to check the endpoints. Right? So next, when a is equal to minus 3, you check what are the roots. Right? Roots are 1 and 1 again. Right? So when you put a is equal to minus 3, you get z is equal to 1 and minus of minus 1, that is plus 1. Right? So a cannot be minus 3. Right? So you can see that if a is equal to minus 3, you get multiple roots, right? Not simple root. So you cannot have a is equal to minus 3. Next, if a is equal to minus 1, right? Roots are 1 and minus 1. And when you put a is equal to -1, roots are 1 and -1. So that is okay. Right? Because 1 is a different root, -1 is a different root, so they are two, both of them are simple. So clearly you know that on -3 between a is between -3 and 1, right? Sorry, -1. Huh? When a is between -3 and 1, not including -3, the method is zero stable, right? So now you know convergence. So the method is convergent for a strictly greater than -3 and less or equal to -1, because it is already consistent for any a, right? So for consistency you have no requirement on a, right? But for zero stability you should have a between -3 and -1, not including -3. So that should be the range for a for the convergence, right? So that is the answer for the first part. Second part is not hard. You have to continue finding C2, C3, C4, all of them, and until you get C depending on A, right? So you can find C2, right? So that is and C2 is 1/2 alpha 2 plus, sorry, alpha 1 plus 4 alpha 2 plus beta 2 plus beta 1. And so you can calculate that. And so you know what is C, alpha and beta. And you calculate that, and if you get 0, then you go to C3, right? So you go until you get a non-zero term. And so that is what they are asking, because you compute until you get a value which depending on A, right? So I believe C2 will be 0 irrespective of A, but C3 might not be. You can continue work on this and check which one is the minimum order you can get independent of A. Okay, so that is how you answer the second part. That is more like finding the order of the method, right? So which you have already done. So I will stop here, and we are almost finished with the syllabus for your course, right? So we will stop with this part, and what we are going to do is we will try to do the tutorial in the next week, right? And after you come back, I will talk to you about how to conduct the ICA and everything, because ICA will be conducted on the after your first exam, first semester examination. That is what I believe, right? So after you come back, I will talk to you whenever there is a crash course for your course, right? Up to that, next week we will do some tutorial problem, right? So that is what the plan is. So we will finish the syllabus with this exam. So next week, if about the tutorial, we will inform you on the group.